Okay, let's talk about scalability and what that means and why it's important to us and ways we might go about addressing it. Scalability, another definition, is the ability to maintain near constant quality of service in the face of different and usually what we mean is increasing loads. Could be scale up, could be scale down. Usually, when you say scalability by itself, you're talking about scaling up, accommodating a higher load, a higher traffic to your web application. One way people think about it, the app should gracefully degrade in the face of increasing demand under constant resources. So you haven't increased the resources, no more memory, no more CPU or anything like that, but you're getting more demand, more requests hitting it. Graceful degradation means that you have a slow and graceful drop off in the quality of your service, not a catastrophic failure. Right? Pages still get served, maybe they get served slower if that's your performance guarantee. They don't just crash the server and start returning errors back to the user. So that's a fault tolerant viewpoint. The system should be able to handle that bursty traffic that's natural on the internet and stress periods without failure, just a reduced quality of service and one that's proportional, if you will, to the nature of the load that's being thrown at it. Another way to think of it is the ability to add resources to a deployed environment to handle the increasing load. So scalability can be the ability to add more RAM and more CPU. And I like this definition because this is an architectural viewpoint, and that the system should be designed in such a way that an organization can allocate resources according to expected need. In a sense, it's designed for elasticity. If you have an architecture such that adding more CPU, CPU to it, adding more memory to it, still doesn't fundamentally change its ability to handle load, then you don't have something that is inherently scalable in its design and in its architecture. Taken together, these two perspectives, the graceful degradation as well as the ability to add resources, broadly interpreted, motivate virtualization services or cloud computing, or what we talked about with containerization. In this approach, resources are allocated on demand, elasticity based on the traffic patterns, and capacity models are created and resources allocated under a service model for which providers assign a fee. You're willing to pay more to handle more demand because your more demand is supposed to be a good thing that you're monetizing yourself, right? So you're paying part of it back to have more resources, but you're getting the benefits of revenue at scale as well. That's basically what that's supposed to mean. I want to talk briefly about 5 scalability patterns. I use the term patterns a lot. These are patterns in the broad sense of what we talk about with design patterns, and by broad sense, I mean they are a reusable solution in context. Our context are server-side driven web applications and services. And so I'll use patterns in that term, but it's not a design pattern like there's a coding idiom behind here and a specific set of things you do programming wise. These patterns are, in fact, have more to do with how things are architected from an IT infrastructure perspective than anything else. Um, so 5 patterns to help with quality of service attributes. First pattern is simply replication. If I can replicate the web application across several container instances, where a container here is meant in our servlet container sense, a Tomcat container. Container instances are mapped to many computational nodes. What's supposed to be represented here is kind of a mini of what you've done in your environment. There's a load balancer in front of your application server, your Tomcats, but you have a multiple Tomcats running on a single processing node. The purple represents a processing node, a computer, a server, what have you, a bounded set of computational resources. And sometimes you may need to run multiple application server instances as an infrastructure service to be fault tolerant, for example, or to make best use of those resources because maybe there's an inherent scaling limitation in your application server. This is the most common pattern for scalability. Some issues with that: if you are doing something stateful on the server side, state's always very difficult because state right now we're managing from a server side state programming perspective inside the runtime environment, which for us would be one of these light blue Tomcat boxes. Right, so if I redirect another request in the same conversational state, for example, to a different Tomcat, I'm not going to have that context. I'm not going to have that conversation going with that particular instance. The second are shared resources. I don't show any shared resources behind here, but what if the Tomcats are all sharing the same disk resource on a computational node? Or what if all of them across this array of 5 are all sharing the same database? I could still be, I may think I'm being cute by replicating here and scaling out this tier in an n-tier architecture, but in fact creating bottlenecks elsewhere in the architecture if they all share the same resource. Second pattern, clustering, and we gave a definition of clustering. Ability to assign multiple computing resources to a single logical service. My ability to take and call this an app service with a fuzzy boundary around it with multiple Tomcats, but from the perspective of the clients of this, what would the clients of this be? Maybe we have a tier in here that's our web server tier, our HP server, right? And it doesn't have to know about multiple Tomcats. It only knows of a clustered service. Clustering allows you to present multiple copies of this service as a single service, meaning a single endpoint, if you want to think of it that way, even though we've resourced it through replication, I'm showing here, behind the scenes. A database, this is very common to have database clusters. Tomcat, by the way, has the ability to cluster. We haven't talked about that in this particular class. We may have a content proxy or a caching proxy, as it's called, for content delivery. You see this in CDNs or content distribution networks. Or we have database services where we have multiple copies of a database mirrored, or we may be trying to scale our database across multiple computational nodes by mirroring, again, a replicated database and doing some kind of sharding or vertical fragmentation between those instances. But in either event, what we're talking about here is that there is some client of this service, and I'm saying client generically. It could be the browser, it could be a piece of server-side code, it could be another tier in our architecture that sees one interface to this, or one interface to this, or whatever service we're talking about. In other words, it doesn't know that there's 2 of these here, 3 of these here, and 2 of these here. And you can perhaps add more of these things. All right, there's usually an upper bound to how many nodes you can put in a cluster. But I'm basically doing a facade pattern where I'm not demonstrating how many actual instances are running behind the scenes, because I'm presenting it as one logical service with one logical interface, which for us means one endpoint for that service. Third pattern, horizontal and vertical fragmentation. I need to spend a little time talking about this. A common mistake in a web application is to view many applications as one application. To look at that website and say it's all one application. We could take Blackboard behind the scenes, right? Here's week 7 of Blackboard that you're looking at. Blackboard has a lot of different learning management systems, or a classic use case of this. We have a lot of different functions that go on in a learning management system. You're getting delivered exams through it. You're using different tools, video playback tools. You're using straightforward content management services in order to deliver content and view it, and for me to post it. External integrated tools through something called the LMI interface, whatever it is. But the point is that it's more portalish. Think my issue as well. There's a lot of different applications rolled into logically one. They look the same because they're all branded the same. They use the same skinning and theming to them, if you will. But we should think of these things as different applications and try and optimize them as such. All right, we can do that from the user perspective, meaning we can look at different user scenarios and permissions around them and features around them. We can look at them from the functional perspective, different types of operations. So again, from an e-learning application perspective, I already gave you some functional examples. User type examples is, what's the difference between showing it for professors and instructors, for TAs, for advising staff versus showing it for students. When you can identify, we've been talking a lot about horizontal tiering, right? That's the n-tier architecture principle. The vertical fragmentation is something different. It's looking at it by identifying these perspectives and componentizing the application into its own respective runtime environment so that you can assign optimal resources to it and code it in such a way that it's optimal. I could tell you in industry, I worked on a large-scale e-learning platform, and the computational footprint behind delivering an exam and grading an exam was much, much different than delivering curriculum in terms of how much CPU used, how much memory used, how many database accesses that it would require. So we identify those different perspectives, and we literally host them on different computational environments, each one of those applications, but made it look as if it was all part of one application behind one URL. All right. So you get that cohesiveness to it, if you will, by sharing your usability metaphors, your visual elements, branding, skinning, and even proxying behind a single URL and doing our delegation like we do in MVC to the different behind-the-scenes services in that way. To a certain extent, microservices will be like that because we're going to use choreography behind the scenes to go take advantage of what the different microservices provide, all while not affecting how the app looks on the glass, if you will. And then you can combine horizontal and vertical fragmentation. So what we do in horizontal, so before when we were talking about a load balancer up here, okay, this load balancer, and let me get my magic pen again, right? We're talking about replicated, right? We did replication here. Here we did replication provided one logical interface behind things. All right, what we're talking about with horizontal and vertical fragmentation, with combining them, is this is vertical, right? These lines here are meant to represent vertical, and these are different functions, all right? So in the learning management system, that might be when we talk about. This might have been for single sign-on or authentication. This may be to take tests. This may be to render the gradebook and reports, which is always computationally expensive in the learning system. And this could be to do content management functions and internal CMS on there. Those are different broad responsibilities or functions of the system, each with their own internal components. But I may have services that are horizontally replicated and scaled that are shared across these things. A common logging service, a common transaction service, a common, you name it, service, whatever I need type of service, and including perhaps even horizontally scaled databases. So I can combine this vertical aspect and this horizontal aspect into one unifying architecture and shared resources behind the scene very carefully. That's why this diagram will show well, but that's why there's vertical lines here and horizontal lines in tiers here. So I have, from a tiering perspective, I have 1, 2, 3, 4 tiers. From a vertical functional perspective, I have 1, 2, 3, 4 functions with their corresponding components. All right, so I kind of have this matrixed approach, which again is something we can actually map our microservices onto quite easily as well if we choose to do so. But anytime we're going to share those resources in that horizontally scaled architecture, we have to be aware about creating our monolith again. But there can be economies of scale sharing resources as well. Pattern 4, virtual machines and containers, right? So we talked in definitions about elasticity. We talked about a little bit more with scalability, scaling up, scaling down, right? We talk about PerfScale measures and technology drivers associated with them, meaning, we talk about the nature of the traffic that comes in. We talk about CPU and RAM and those resources and how much a Java program is going to consume and how much a functional thing like a gradebook is going to consume. Well, what about cost? All right. Traditionally, your operations group creates a cost model based on a cost per transaction, a logical transaction. That could be for us an HTTP round trip. It could be a database transaction. It could be a conversational state transaction, a long-running transaction. It could be the collection of HTTP requests used to do a single page. And that's always kind of been the traditional one for web applications, is to look at the cost of rendering an individual page. And that's, of course, changed over time with all the more dynamic aspects of fetching content and doing DOM manipulation on the client, which we'll get to in a second. Wasted capital costs are traditionally measured by computing resource idle time. If the CPU is idle, if I'm not making good utilization of my memory, then I've got a problem, because I've basically capacity planned for my peak load, and anything that's unused in CPU cycles, I'm already paying for. I want to maximize the dollars I spent on CPU cycles by making sure they're not sitting idle. All right. So if that's the case, instead of trying to always push the limits, because I have this, the fundamental problem, and let me bring up my notebook here for a second. And I'll give you one of my horribly drawn sketches again. Let me bring this up. The fundamental problem is if you look at the nature of traffic on sites, it is very often bursty, right? You go along, you get some traffic pattern, boom, you get hit with some site, and it looks almost like this, heartbeat, EEG kind of thing. And sometimes, and the time difference in here, this could show one day. right? And maybe you get peak traffic because you're doing a system, a learning management system for K through 12 that has subscribed to math class, and this is math class section 1 and math class section 2. Or it could be over a long period of time, like a whole year, 1 year down here, where this is start of fall semester, this is start spring, and this is start of summer session. Okay, so you have these periodic nature of some websites where you can predict bursty traffic, and other times you just have what's called historically called the slash dot effect. Not as many folks do slash dot as much as they used to. Maybe you should call it the Reddit effect. But a story would appear on slash dot, and all of a sudden, what it was talking about would see an instant spike in its traffic, and have it go down when whatever this slash dot article was about. It would refer out to that website, and this website would say slash dot refer to site, and all of a sudden this website would go down because they were planning for this load. All right, so that was always called the slash dot effect. But the nature is very rarely do you have this predictable, consistent traffic to your website. Okay, so that makes capacity planning difficult. Are you going to plan for this? Are you going to buy all the resources to support this? Or to support this because it's yearly, or to support for the slash dot effect? Or would you rather say, I'm going to pay for those cycles when I need them? And that's the cloud computing model, right? It supports elasticity by providing computing resources on demand. You often hear, we're not going to talk really cloud computing in here. You often hear about three models with it: software as a service, platform as a service, and infrastructure as a service. In this class, realize out of those acronyms, we're really talking about infrastructure as a service, your ability to use those cloud services to host your own applications. You might be using some of a platform as a service, some of the built-in services, if you're on Amazon, a DynamoDB or something like that. But we're not talking about software as a service, something like Google Docs or the like of that. So we're talking about leveraging that infrastructure as a service and paying more as demand increases, and be willing to pay more. Now realize that the cost per transaction that Ops is traditionally worried about goes way up with a cloud computing model. I mean, they're going to charge you more per typical transaction because that's how they make their money, right? But they're hoping that they try and spec out the cost model, so ultimately you're saving money while they're getting scale of multiple customers on the same set of computational resources. I find some of the discussion around the cloud sometimes funny with people because it's almost like they think the cloud's just magic, like it's this nebulous thing that magically produces computing resources on demand. I mean, realize no matter where your program is, it's not the matrix. It's running somewhere. It's running on some physical server somewhere, maybe a virtual machine inside of that cloud-based server, or a container running on top of it. But there's some physical CPU somewhere that's executing those instructions that you wrote. And the cloud gives you a lot of flexibility and elasticity and all those things, and multi-tenancy and all these concepts. But realize eventually somewhere's got a big bank of servers that they're dynamically allocating. All right, and that's part of the value that the cloud gives as well. It's not just elasticity and scale; it's also things like fault tolerance, and different qualities of service that you can get from different flavors of the cloud. So, for example, my research, we do mobile health applications. We need some more protected services around for privacy of data, so we pay for a higher quality of service in order to do that. All right. You achieve cost benefits in a lot of different ways. I just talked about them. Reduced total cost of ownership. I don't have to worry about the purchasing process. I don't have to worry about the wire-to-wall process. I don't have to make sure these things are plugged in. I don't have to replace servers that fail or disks that fail or any other computing resources that fail. And I don't have to physically house the iron anywhere. Somebody else has got it. I pay as I go, and I have the ability to scale up by spinning up new VMs and containers. And then the containerization benefits of speed we discussed before. Things like avoiding the dependencies in the matrix of hell, having to put the dev team support products, doing continuous deployment, and the like, is all synergistic with the notion of cloud computing. It is typically your chief operations or chief CI. It could be your COO, it could be your CIO. It depends on your organization. It could be your CTO, but there's usually a C-level executive that has decided on the right infrastructure as a service, if they're using the cloud, or whether to go old school with buying your own iron or renting rack space somewhere. But what decision they make from an IT infrastructure infrastructure, right? This is all IT infrastructure. You as a software engineer should be certainly can be aware and do some things programming wise, like microservices, for example, to take advantage of the IaaS, if you will. But it's ultimately a chief information technology officer's decision, usually for the organization, as to what you're actually going to be hosted on and how you're going to pay for it. And then finally, pattern 5 is maximizing client processing. Those of you who took 421 with me, this is the part where we talk about shifting that MVC pattern from the server down to the client. This is more about REST, putting state in band so we can be stateless on the server. Realize when we shift more processing to the server, one is our requests when we shift more requests to the client, our request handling on the server tends to become more stateless, which means we don't have to hang on to particularly the memory resources or use sticky sessions, dedicate traffic to particular servers because they're running in a particular VM, so we can find that HTTP session object. It's also good for the server because we're basically no longer using our CPU cycles for certain things. We're using the clients, right? The client can do some of the logic in the JavaScript in the browser. The client can do the rendering of the presentation layer. Through DOM manipulation and CSS processing in the browser, and I'm no longer doing all that in the server. So guess what? I'm paying for less cycles, and I'm using the consumer's cycles. Realize that our drive toward buying more and more phones that with heavier processors and so forth is our part of the economics of buying more. So that the servers do less, right? It's not a benefit for us if you think about it. It's actually a benefit for those who are providing the services. So is it so good for the client? Well, initially these technologies enhance user experience, but there's other kinds of issues that come up, differences in client-side platform processing. My phone's not like your phone kind of thing. A heavier processing burden on the client means it's harder to manage performance expectations. So as a service provider, I'm always concerned about what it's going to take to load an app or load a page on this device. Especially in the Android side, people bring all kinds of devices to the table. And what do? Do I design and measure against the worst of these devices or the best of these devices? And then there's, of course, a whole new class of security concerns with cross-site scripting, spoofing, and so forth. But it's a resource bargain for server-side provisioning. Use the client's computational resources, and so on the server we can handle more traffic. These are 5 patterns of scalability that you can employ and that can impact what your organization does, both from an IT infrastructure, particularly an IT infrastructure perspective, and also from your software architecture perspective.